Hi there, my name's Bijou Smith. The handle is a Chronon Master. This is another in my series of showing you that the New Zealand NCEA exams are not really as well, they're not really as fair as they should be. In other words, basically I'm going to go through this raw without having looked at this exam and as a professional tutor, I guess. Because I haven't looked at the physics paper before, I haven't done any tutoring for this over the last few years, I guess. This will be a little bit like a simulation of what it might be for a student, just a normal average student. And if I cannot do this in about 1.5 hours, then I don't think any student should be expected to do it. If you have 3 hours for the total exam, you do 3 achievement standards. It really should be 3 times 1.5, right? So you should get about 5 to 6 hours. I reckon 5 to 6 hours to do the exam. And so if they only give you 3 hours, they're giving you half the time, roughly. I reckon. It's no skin off their nose to spread the exams out a little bit and to give students more time. I don't think it's unfair. You could sort of have a whole half a day for one exam per day. I know the logistics can expand the number of weeks for the exams, but they could go into December and so on. That's my political statement. But for students who just want to follow this as a kind of tutorial, you'll hear it. You'll get to see all of my kind of thought processes. I try to sort of speak what's sort of in my head, roughly anyway. So let's have a go at this, and if the problems are too easy, just skip ahead, pause the video when you think you can solve the problem yourself, and just unpause and skip ahead if you need some hints. And by the way, because it's raw, I will make a lot of mistakes, and I don't apologize for that. That's part of the learning process, to show you that even an expert can make mistakes. Okay, especially in an exam situation where I'm not going to rely on Google or anything. I might have my calculator here, I suppose. Well, I'll either use Maxima here, which you can install. Just on GNU Linux, it's apt install Maxima, or I might use Python. Anyway, I've got a Python shell over here open with math, all the math functions I imported. Okay, anyway, let's start. So it's a roundabout rotational motion, and it's a constant angular speed, right? So the rate of change of the angle, theta dot, which is called the angular velocity, is a constant, which means which implies the force is in the radial direction, pulling it back inwards towards the circle each time, each small increment angle, and it will be m times the speed squared over the radius. Show the angular velocity is this much, 1 revolution. So the angular velocity is the rate of change of the angle with respect to time. So 1 revolution is 2 pi radians. So the change of the angle will be 2 pi for 1.23 seconds. Okay, so probably Python is the one to do here, because it goes to decimals. 2 times pi divided by 1.23, 5.108. Now that's exactly 5.11 if we're only doing 3 significant figures. You're allowed to say exact statistical statements, right? radians per second, because we measured the angle in radians, 2 pi. Slows down. Spinning disk rotational inertia, determine the average angular deceleration of the roundabout as it slows down. Calculate the average frictional torque acting on the roundabout. Okay, so this next one. It's a roundabout. Stops pushing. 30 seconds later, slowed down. Okay, I think you want to find the average angular acceleration, deceleration, negative. Well, so you might think of drawing an acceleration time graph, but what you really want is the velocity or angular velocity time graph, because the slope of this will be the angular acceleration. So what we have, we start with, maybe we should look at the final angular acceleration. So it'll be 2 pi over 2.04 now. Let's call it 3.08 radians per second. 3 significant figures. Now that means we go from, what was it, 5.11 down to 3.08, not to scale. 30 seconds, right? So down here we assume that maybe they go back to constant driving at a constant rate, but here it could go down like that, like very fast deceleration at the beginning and then slower at the end, or it could go the opposite way like that, or it could go like this, or they could go down quickly and then very slowly, or whatever. But the average is determined by the straight line. That's not very straight line. So the slope, the average angular acceleration will be this slope. In other words, you only look at the final and initial and final points for the average. You don't actually care what happens in between. You just don't care. It doesn't have to be even a straight line. So let's actually not make it a straight line. Let's just make it a dashed line, right? It just goes from one to the other. You do not care how. So it's going to be the slope, which is 5.11 minus 3.08 divided by the horizontal interval, which is 30 seconds. Alright, so it's going to be, we can write it exactly equals if we do statistics, right? Minus divided by 30. Well, let's do it exactly. The 2 pi will be out the front, and divided by I'm going to write it out in full so don't make any mistakes. 1 divided by, what was it again? 1.23 minus 1 divided by 2.04. Oh, what the heck? Multiplication there. Let's call it 676, right? 676. 0.06762, 3 significant figures. Okay, well that's radians per second squared to 3 significant figures to calculate the average frictional torque. Yeah, okay, so the average, so the torque equals the moment of inertia times alpha, but that could be changing from moment to moment. However, if we take averages, and the moment of inertia is constant, 57.6. We can just say that the relationship is that, so it'll be 57.6 times 0.0676. Okay, I guess I could take my previous answer and just multiply by 57.6. It's 3.89. If we round up, yeah, 3.89. What? 3.894. Okay, that'll be units of the moment of inertia, kilogram meter squared, and then radians per second squared, but usually you don't worry with the radians. Okay, this is like the ice skater problem, where ice skater pulls their hands in close to their chest and they spin up fast, so they want to speed up. So you can't push themselves faster, so they have to they can move towards the center. To reduce the moment of inertia, so that the moment of inertia after they move is less than before they move. We have to explain this. That's the intuition. There are no external torques is the key thing, which means that the Newton's second law is that a torque equals the change in the angular momentum over the change in time. So that means that's equal to 0, so the change in angular momentum is 0, so it's conserved. So the final angular momentum equals the initial angular momentum. But what is the angular momentum? It's the rotational inertia times the angular velocity. So it doesn't matter how it slows down. The beginning and end points are the only parts that we're interested in. The initial and final points, right? So that means the final angular velocity will be equal to the initial moment of inertia times the initial angular velocity divided by the final moment of inertia. Now, because this is bigger, the final inertia is bigger than the initial inertia, this fraction is going to be greater than 1. So it's going to be greater than the initial angular momentum. So it speeds up. Speeds up in terms of angular velocities. I think that's all you really need to say about that. Tilda wants to jump to roundabout. Okay, so the final angular velocity will be proportional to the angular acceleration. Angular acceleration equals the rate of change of velocity. So the change in the velocity of the roundabouts, even if, okay, so it's initially stationary. So omega I equals 0. So the change is just going to be omega f is equal to that angular acceleration times the time. But angular acceleration is proportional to the torque, tau, which equals the force times the perpendicular distance over which the force acts. And the force is equal to the rate of change of her momentum, which is the same in both cases. She goes from fast to slow over, we'll assume the same time, same speed and so forth. Assume also the same time. Same time at which the momentum, her linear momentum, goes from whatever it is down to 0. So yeah, so starting at O, the perpendicular distance to B, call that the perpendicular distance, and then to A it's like this, perpendicular distance from O to A, the center of the circle. Okay, but D perpendicular is the perpendicular force lever distance from the pivot, from the center, which we've called O, but the perpendicular, sorry, not I, perpendicular for A is greater than the perpendicular distance for B, and so therefore the torque for A is greater than the applied torque for the jump B. Therefore jump A will speed up around about more than jump B. Following our chain of reasoning backwards, back to the change in the back to the angular acceleration and the change in the angular velocity being proportional to the acceleration. Oh, this is a little tricky. So there's some V here. V equals R omega. This will be a constant if if she just continued on without so I guess you could say with respect to the roundabout at center O, Matilda's angular momentum is going to be equal to the her mass times r squared, the radius, times omega, which is v over r. So that's mrv, whatever the initial v is when she moves off here, v naught, let's say. I don't know what to call it. Yeah, so let's say there's no external torque again. Alright, and then that means that the change in angular momentum for the total system equals 0. Okay, but you could argue that so let's say the total angular momentum initially is moment of inertia of the Matilda plus the roundabout times the angular velocity initially of the roundabout. Since they're both going at the same rate, she's attached to the pole. So that's going to be equal to the final total angular momentum. Let's call it final total. But this is different. It's composed of the rotation of the roundabout. That's m times the roundabout final plus moment of inertia of Matilda, which is changing, I guess, now because she's getting further distance as a function of time from the roundabout, and her the perpendicular component of the velocity r omega is changing as well. So But ultimately, she never gets past this angle here, right? She can go out to infinity in this direction. There's Matilda. And, eventually infinity's her angular velocity is decreasing. But any subsequent motion in between can have no effect on the roundabout because there's no torque. There's no extra torque acting on the roundabout. So it should be as if... Oh, sorry. So let's do it the other way around. Let's do the roundabout and then Matilda. Doesn't matter which way, but this is the roundabout here. But then Matilda is... she's got a separate angular speed, but that's equal to 0 because she's not kind of going around the circle anymore, at least ultimately. But like I said, it's going to have no effect on the motion of the roundabout in between. So that means the final angular velocity of the roundabout is going to be the left hand side here, both their moments of inertia times the initial angular velocity divided by the rotational inertia of the roundabout. Now the moment of inertia is positive numbers, so that's just going to be the denominator here is bigger than the numerator, so that's going to be greater than the initial for the roundabout. Therefore, all of the effects. So just you could say naively, the roundabout should speed up. Yeah, so yeah, that's bigger. Should speed up a little. But you might not notice it because... But if the moment of inertia of Matilda is much less than the moment of inertia of the roundabout, this might not be noticeable. And it's like other possible effects. Yeah, there could be other effects that come into play, I guess. But I'm not going to discuss them here. Well, maybe I should come back to this later and think about that a bit more. It's like, because it does say she slips off frictionlessly, so yeah. So it acts as if there's a little bit of torque on the roundabout as she comes off, just because the moments of inertia of the total system change. Not the total system, but the angular velocity of Matilda changes. It's going to go to 0 ultimately. I think that's how you'd answer it. I'll come back to that later, maybe. That's 'cause it's been a while since I've done these sorts of questions. Okay, let's have a look at this one. This looks like a conservation of momentum problem. There's a collision, stationary collision. Okay, comets and asteroids. There's no air resistance or anything. The question, of course, is whether it breaks up and cracks up, which is going to be an inelastic kind of thing. But anyway, distance to the center of the mass when the objects are this far apart. Okay. Position of the center of mass, let's call it the x direction, right? It's like an average. So you like, when you get an average, you want to sum up the masses, each mass I, times its distance, position times its position, and then divide by this is called the weight. Mass is a weight on the position, if you like. and just divide by the sum of the masses. So that's just going to be m1 x1 plus m2 x2. There's only two masses, divided by m1 plus m2. Now, okay, 4 meters apart. So we could just call this x equals 0 here. Yeah, so it'll just be the second mass, 3 times 10 to the 2 kilograms times 4. Let's just say that's equal to 0. 4,000, right? Divided by the sum of the masses. That's 300 plus 100. Let's cancel a few zeros there. So it'll be cancel the 4. So you get a 1 there, a 10 here. So 3,000. Meters. Uh, 3,000 meters over here. Center of mass, 3,000. But they're 4,000 apart, so the distance from the first thing is going to be 1,000. Distance of the center of mass from, they call that M1, they call that M2. From M2 is 1,000 meters. So this is from M1. Okay. Force of gravity is G M1 M2 over R squared. Do we have Newton's constant? I'm assuming it's in your formula sheets. I'm gonna assume from your formula sheet you've got 6.67. That'll be newtons per kilogram squared meters squared. So 6.67 minus 11, and then what were they again? 300, 100 and 300 kilograms divided by the distance squared, which was 4,000 meters. Excuse me. Well, calculator time. They're 4,000 meters apart. I guess gravitational force is pretty puny, but that's extraordinarily puny, isn't it? Anyway, 1.25 times 10 to minus 13. Newtons. Oh, 10 meters apart. What am I doing? 10 meters apart. Should be a lot bigger. 10 squared. 2 times 10 to the minus 8 newtons. To the two significant figures, 2.0. Why do we have to assume the velocity is a constant before the collision? Assume the velocities of the mass is a constant. Wait a minute, am I missing something? I don't see why we have to worry about that assumption. Think about that. Anyway, find the acceleration at this separation to determine whether the assumption that the velocity is constant before the collision is valid. Okay, so acceleration, velocity is a constant. Acceleration is approximately 0. So acceleration is force divided by the mass. So the larger acceleration will be for the smaller mass. 2 times 10 to the minus 8 divided by that's relative to the observer watching the system. Smaller mass would be 100. Okay, the force of gravity only acts on each mass separately. A mass 1. Okay, so acceleration on the ith thing. A force on the ith particle. Well, yeah, that's pretty small, right? That's another 2. So that's 2 times 10 to the minus 8, 9, 10, right? Meters per second squared. Assumption that the velocity is a constant before the collision is valid. And the actual velocity is going to be a bit more than 5 times 10 to the 2. From the assumption v approximately constant. Approximately 500 meters per second. This acceleration due to gravity will not significantly change the velocity. Until roughly a time to collision around about well, we want it to be about 1 meter per second. That might change it. So to get like a change in velocity of about 1 meter per second, we would have to have change in v equals acceleration times change in time. So this would have to be, change in time would have to be about 10 to the 10 seconds, which is much greater than the collision time. Okay, so time to collision at an absolute maximum would be equal to the distance. Okay, time to collision what do you call the velocity times the distance roughly, so it's going to be about 500 times 4,000, which is 2 times 10 to the 1, 2, 3, 4, 5, 6, 2 times 10 to the 6 seconds. So it'll take a while, but it's nowhere near there now. So it's nowhere near 10 to the 10. Actually, it's 10 to the 10 seconds. So yeah, it looks valid. It's like the difference between 10 to the 6 and 10 to the 10, 10 to the 4, 10,000. So we're going to change the velocity in at most like the second decimal place. So it might change it by plus or minus a millimeter or something like that. A millimeter per second. Objects collide with no external forces. Smooch together and then move away. Show that the size of the momentum of the rocks A and B are the same. Okay, but they're the same mass. Slightly unrealistic. Same angle too. I'm not sure how much detail we want for this. Hang on, is one of the rocks moving? Okay, so maybe suppose the first rock is at rest, say V2. So initially we got M2 M1 V1 500 meters per second, and we've got M2, which is a bit bigger, right? V2 equals 0. Okay, so the initial momentum equals, as a vector, equals so freaking heck, 100 kilograms. What's the other one? 400 was it? 300. Should have mass conserved, so it should add up to 400 kgs. So it'll be 5 times 1 times 10 to the 4. So it'll be 5 times 10 to the 4 in the x direction. Oh, computer froze up there for a second. Yeah, so I don't know. What do we have to show? Show that the size of the rocks are the same, even though they are in different directions. Size of the momentum of the rocks. Okay. Well. The total, the momentum. So where is it? No external forces. Some of the we probably don't need that on the diagram. Sum of the external forces equals 0, which implies the change in momentum equals 0, which implies the momentum initial equals the momentum final. So we've got momentum initial. How do we draw this? Maybe go to some arrows or something. Here we go. So that's the initial momentum. Sorry. In the x direction. This is the final momentum for PA. This is the final momentum for PB. Okay, so PA plus PB plus PB had better be equal to the initial momentum as a vector. Okay, so that's the final momentum. Now, to draw those, PA is like that, and PB is like that. Roughly, I haven't drawn it exactly. PA, PB. Now, what do we show that the size and the momentum of the rocks are the same? Alright, so that's a 20 degrees. And this one here is 20 degrees. Hang on. Let's draw a slightly better diagram here. Okay. Now, is that enough information to show that they're equal? Okay, so that means this angle here is 90. So what's that? 20. That's 110. So this is going to be 70 degrees. This one has to be 70 degrees. So this one has to be 20 degrees. So by isosceles triangles, the side length A has to be the side length B as required. Now we could prove this using some fancy vector notations and so forth, but we don't really need to. Like, you can use if you like, you can use, this is going to be, I don't know, what would you like to use? Size of the momentum of the rocks. You could just use the fact that this is PA sine of 20 degrees if you wanted to, and this length here from here to here is PB sine of 20 degrees, and they have to be equal, so sine of 20 will cancel and you'll just get left with PB equals PA. That's because the PB in the y direction has to be equal and opposite. So PA in the y direction, PA in the y direction plus PB in the y direction must be equal to 0, because that's the initial momentum in the y direction. That's another way of doing a problem. But since we draw vector diagrams, that's also a fine way to do it. Okay, well, PA is the same as PB. That's equal to the mass times the velocity. Okay, but we've got, for example, PA here, and it's at 20 degrees. And we know that the x component, so twice the x component must be equal to the initial velocity in the x direction, which is, what was it? Initial momentum 5 times 10 to the 4. Okay, so that means px has to be equal to 2.5 times 10 to the 4 kilogram meters per second. And so therefore the hypotenuse, which is the length of the momentum vector, is going to be px cosine of 20 degrees. Sorry. and I guess we have to put that into our calculator. But I'm going to have to convert to degrees. So it's 2.5 times 10 to the 4. By the way, that's, you know, that's shorthand for that. Times cosine of 20 times pi divided by 180. I have to do the manual conversion to radians. 23492. Kilogram meters per second. Therefore, the velocity, which is equal to the absolute value of the momentum divided by the mass, is 23492 divided by 2000, right? Oh, 200. I'll do equals because I can just do significant figures. I gotta put brackets around all of that. 117.5, so I'll round that to 117. Meters per second to 3 significant figures. I didn't need all that space. Make it bigger. The symmetric. That's just a note for the diagram there. That's why we get the 2. So the total sum of the px equals 2 times px. Sum of the momentums in the x direction. And so we can talk about either particle, A or B, it doesn't matter. Alright, I think that's it. Calculate the speed. Yep. So all we had to do is respect the fact that the speed is at some angle, so yeah. Question 3. Space explorers on Mars. Time for a cup of tea, I think. Simple harmonic motion question, looks like pendulum. Got the mass. Since they don't give you a lot of space there, I assume you got a formula sheet for this, but let me go off on an excursion here. Of course, you would never do this in the exam, but I think they might give you, I don't know what they give you. They might give you a formula square root of k over m for a pendulum, but that's not really a pendulum, that's a spring. For a pendulum, I think it's dimensional units, right? Per second, newtons per kilogram. This will be divided by L. Okay, so what's newtons? Kilogram, meters per second squared. Kilograms to the -1 for G. Meters per second squared divided by meters, because it's second squared, and the square root of that is per second. Yes, that's dimensionally correct for the gravitational pendulum. Although this will be G for Mars, I guess. Different. But let me show you how to get that. I think so. We got the pendulum here. Let's do a big long vector for mg, and then draw a few triangles for help. So this will be, I think, for us, if I remember correctly, small angles only. Small angles, just keep this in mind, that sine of theta is approximately equal to theta, the angle in radians, that is. So yeah. If we want to derive a simple harmonic motion restoring force thing, we want to say that the tension along the string isn't moving, so there's a tension force here, and that'll be balanced by the component of gravity that's parallel to that, which means there's this extra force here, and of course by similar triangles you know that that's theta. If you don't know that basic Euclidean geometry, let me know in the comments if you need a tutorial on that, but you shouldn't. So by simple sines, that'll be mg times sine theta along here. So that'll be a kind of a force on here. So let's just look at the pendulum. There's a balance of forces in that direction, but in the perpendicular direction there's a force mg times sine of theta. Okay. Yeah, so we could draw another one of these triangles where that would be theta, and so we could have the force in the x direction being mg sine theta times cos theta and all that sort of thing. Do we want to do that? Cosine theta and a sine theta. What I could do instead is look at the displacement from the equilibrium position and call that x. Low would be, remember it's going to be negative x, right? It's the x, positive x in that direction. So I've drawn this kind of the wrong way around if you like. But let's call that x. And remember the angle theta up here. Sorry, I'm getting the diagrams overlapping. Okay, now if we imagine going along the arc of a circle, an arc length s would be equal to the length of the pendulum times the angle theta, but that's approximately equal to x, or if you like, x would be equal to L sine theta, which is approximately equal to L times theta, which is approximately equal to the arc length around the curved arc, if you like. Do I need to use that? I'm not sure. Anyway, okay, so we could. Okay, so I think I can see. So I could say x over L equals sine theta, and so I could use that in terms of the restoring force roughly in the x direction. It's not exactly in the x direction, right? There's a sort of a matter of the angle here, but for small angles, the restoring force in the x direction would be negative x, because remember here x is negative, so it would be negative mg times x over L, roughly. Let's write that as minus mg over L times x. So this is only approximate, right, for small angle approximation. I'm not sure if this is the way they do in the textbooks, but this is the way I'm doing it. So I'm making an approximation here, and then that is like a simple harmonic motion, like a spring. Okay, Hooke's law. We've got F over m which equals the acceleration is negative g over L times x. So it's like a spring, but not exactly, because we've used the approximation. Like a spring with the spring constant equal to g over L. But do you solve the spring equation like that? So what you do is you know that there's a solution to these types of equations like this, where the second derivative is proportional to the quantity itself. And these always have a solution which can be given by a phasor representation, a e to the I omega t. Remember the two dots here is d by dt squared, d2 by dt squared, double dots on something. So there's a time here, if we double integrate, we get an exponential. Okay, so that means if we exponentiate that to find out what the constant of integration a is here, we would get an I and an omega a e to the I omega t. Alright, that's because the derivative of e to the t is just e to the t. So you just do a chain rule here. And then trivial chain rule, because I and omega are constants. Now that means another derivative brings an I times an I, that's a negative 1, and omega times omega, e to the I omega t. But this bit here was equal to x, so that's just minus omega squared x. Okay, but the acceleration was also negative g over L times x. Okay, so just looking at that, it means omega is the square root of g over L, which is what I guessed would be in your formula sheet here. I don't think you expected to do this in the exam, but anyway, this is one way to solve the problem. So you also might find that period equals 2 pi over omega in your exam, and omega equals square root of g over L. Now, gravitational strength 3.72 over 1.83. If they ask you for approximations and all that, you can say small angle and everything like that. Okay, so 3.72 divided by 1.83. Yeah, 1 point. Okay, and let's just do 2 pi divided by that. .4257. Therefore, the period is equal to 4.4 to two significant figures. And so it don't need to know the mass for this simple pendulum. Simple pendulum will assume a small angle, small theta. Now, okay, that'll be this position here, 0.3 meters, and then on the other side, negative 0.3 meters, and in between it's just going back and forward like this. Two seconds after it's released. Yeah, so angular frequency equals, or the period, maybe it's better to do the period. So 4.4 seconds to go completely around. 4.4 seconds. So we just need the fraction it goes around to fraction of the 2 pi, the phasor turns. So we're gonna take this as a phasor going around like this, but only the x component matters. It's the x position of the phasor that we're interested in. The phasor is what I did on this page here. This e to the I omega t, z equals e to the I omega t, is a unit complex number, so it's on the unit circle. That's terrible. 1 minus 1 1, I minus I. That z is just one of these things here, depending on omega. Omega is the angle. Sorry, omega times time is the angle. Now, that's the phasor. The fraction of 2 pi the phasor turns is 2 over 4.4, which equals 45, 45, 45. Well, it's 1 over 1.1, right? Sorry, 1 over 2.2. Anyway, whatever that is, 0.4545 recurring. Now, what do we need to know? Determine the position. Okay, so the change in the angle is going to be 0.45 times 2 pi, which is equal to 2.8. Let's keep a few decimal places. 2.856. Yeah. I could say it's 0 there. It rounds up. Now, it's almost finished the calculation. Well, you might the brain might prefer to visualize in terms of degrees, 160 degrees. Well, okay, this is 100. This is 120 here. 160. Well, so it's around about here somewhere. 2.2 seconds. Sorry, 2 seconds. Goes to there. Right, and so using some fancy trigonometry. What do we need to know? Position of the pendulum bar. Yeah, so this is x that we want. X final. Okay, so x final is like the cosine of the complement of the angle there. So let's call that pi minus theta. The length is, what is it? 0.3. Phasor length is unchanged. So it's x final over 0.3 equals cosine of complement of the angle delta theta. Now, what happens? Pi minus. Let's just put the whole thing in here. Now, what happens if you forgot to do the complement of the angle and you just did cosine of theta? You'd expect it to be similar, but on the negative side of the negative x quadrant. So in fact, that wouldn't be too bad. So if you used this geometry here, where you wrongly put delta theta here, what you get is a negative x here. Whereas this is assuming x is like a positive length, because we're actually using this angle here. So in fact, it's maybe more correct. So that's the absolute value of x. That's what I'm really doing. Now, okay, I gotta multiply that by, okay, well, let's just put that in minus 9594. Or you could say x is equal to 0.3 times the cosine of the actual particular angle that we've got, negative 0.3 times that, 2878. Or I was going to say capital B for Bob. .288 meters to the left. To the left, 0.288 meters. 3 significant figures. Okay, it's probably more than enough. I'm trying to not assume that we've solved the equation here, the equation of motion. So maybe in the back of your mind you have that the x position is equal to negative g over L times x. So the period omega equals square root g over L does not depend upon the amplitude. And I don't know, actually come to think of what is a good explanation, physical explanation for that. Right. I guess it's roughly because this is because the acceleration is proportional to force over mass, and the force is proportional to omega squared, and oh yeah, so it's proportional to the mass times omega squared, right? Omega squared is proportional to the acceleration. So m factors out. Leaving the acceleration, which equals the rate of change of the position double second derivative, is just well, it doesn't really explain it, does it? Portion of omega squared. It just means that the restoration of the motion doesn't depend on the mass. I'll leave it at that. Probably if I try to think more about it, I might get into trouble. Just trying to think of a good physical way to explain it to students, It's a little bit counterintuitive. A lot of people would think, well, if you make It wasn't really to do with the mass, right? It was to do with the period. It doesn't depend on the amplitude. Oh yeah, so what is the amplitude anyway? Oh, the amplitude is whatever it begins with. Amplitude is arbitrary according to this. So I'll just leave it at that. We can just say that the amplitude doesn't depend on G and L. Okay. So what you should say probably better is just that probably this isn't really correct. This is just the hot air. But G and L are physical constants. Actually, not but, because physical constants. So if you've got some quantity that is equal to some function of just physical constants, then it's not going to change. That's the correct way to do it. So I just erase this bit here. That's why. Sorry about wasting the time there. Total energy lost. Maximum velocity of bob for the initial and the final amplitude. Yeah. If you have a thing here, not sure how to start this. Because I'm not sure what the students will sort of have as their background knowledge. I should probably know this, but what it could do is use the simple harmonic motion approximation to this. So uniform circular motion of the phasor is simple harmonic motion of one of the components. And so, if you're going around like this if you got some object sort of moving actually on a circle at some omega, then its velocity or speed is equal to r times omega. Now, in this case, r is not the length of the pendulum, but it's the radius of the oscillation. So here, for the phasor, r for the phasor's circular motion, I call it r in quotes, is just equal to the magnitude, so 0.3, like that. And then okay, so it's the maximum here. Here it's Vx equals 0. It's motionless, and then in the middle it's let's look at the bottom. Here Vx equals r omega. It's for the circular motion of the phasor, for the phasor, not the actual particle on the pendulum. We're just looking at the phasor representation of the motion here. So the maximum velocity it's a maxima here, the bottom, or the top in the negative direction. So V max will be equal to 0.3 r times omega, which is I think we calculated that before. Forget. Wait a minute. What do we do? We use a different formula here. Oh no, G over L. Yeah, so 7.2 over 1.83. Wow, okay. Let's copy that formula down here. Send multiply by 0.3, right? Uh, 4277. Blah blah blah. Yeah. All right. Okay. So Vmax initial, Vmax final is going to be down to 0.2. So it'll be the same phasor diagram, but shrunken down like that. Some velocities will be like this, but that's 0.2 now instead of 0.3. And then it'll be, well, I can just use the same calculation, but 0.2 there. Better be the case that we haven't changed the length of the pendulum, or that we haven't changed the I set the pendulum to 0.3. Oh yeah, so we haven't changed the rotation rate. Omega is, I think omega is still the same. 28515. Okay, so a change in energy total equals change in kinetic energy, because we're not going to worry about the change in potential energy. I'm going to say that that's roughly zero. There's no gravitational change in the energies or anything. So it's a half m Vf squared minus a half m Vi squared, initial squared. It's just a half m Vf squared minus Vi squared. Notice we could have put in the 0.3 and the 0.2 here and the omegas and everything. In fact, let's do that. It'd be omega squared, and then it would be final 0.2 squared minus initial 0.3 squared. We could do it like that if you like. Either way, you could use your calculated velocities here, but I think it's better punching it into the calculator to use the 0.2 and the 0.3, because they're at least exact according to the information. We've got three significant figures here, right? So we could do that, but we need to know the mass. 2.3 kgs. Times whatever it was, omega 3.72 1.83, omega squared 3.72 over 1.83. That was omega squared, remember? So it's much easier to plug it into your calculator using these neater values and get more of a precision answer. 0.5 times 2.3 times 3.72 divided by 1.83. I'll show you in a minute that I don't need the brackets there, but I do need the brackets next. Python knows, about order of operations. I got the final and initial around the wrong way. Oh no, yeah, that's right. It should be negative. Right. So now if I want to do the omega squared in brackets, I certainly could put brackets around there. So it's putting, but you'll see that it knows to do the division here before the multiplication here. Alright, so 1169, let's say, joules would be the units if we figure it out, and total energy loss. loss is approximately 0.17. Oh, sorry, 117 joules to 3 significant figures. Notice that you can say a loss is a positive number. It gets confusing if there's not a loss and you say like there's a gain in energy, then you'd say the loss is negative, which would be like a double negative. So be careful with your language. Speed diagrams. Why do we need this? Oh, yeah, okay. That's it. So hopefully that gives you an idea of how much time it would take a reasonably competent student to do these exams. You could subtract off a bit of the theory that I did here, because we've got this kind of thing probably in your formula sheets. Okay, that's all. Catch you next video.